welcome to my talk. I'm describing today the COSINUS experiment, which is a search for dark matter using cryogenic sodium iodide detectors. So now we have quite a lot of collaborators. We started out with very few institutions, but now we have collaborators from Austria, from Italy, from Finland, and also in China. So the main motivation for the COSINUS experiment is this very old signal, which was measured by the DAMA experiment. Let me switch the slide. Why doesn't this work? There it is. So since several years, the DAMA collaboration reports that they measure this modulation and the rate of events measured in their detectors. So what you see in the plot is basically the modulation of the rate of events in the DAMA LIBRA experiment. And with increasing measurement time, this has even become more and more significant. And this signal is very much consistent with the classical WIMP scenario, so with a heavy freeze-out WIMP on the GeV scale, doing inelastic scattering in the detector. And while there has been no convincing explanation which is not consistent with dark matter, the modulation which they measure is very much consistent with what you would expect from an actual WIMP. So it not only has the correct period and amplitude fitting to this WIMP miracle, but it even has the correct phase. So there's some day where you would expect the rate to be maximal, and even this apparently works. I think my screen sharing was interrupted. Can you still see the screen? Yes, now you should see it again. Yeah, so if you remember the talk from Mark earlier and also from other people in this session, then you might know that there are a lot of different direct detection experiments which actually exclude this signal from the DAMA LIBRA experiment very strongly, so that there is a lot of tension with the results from other experiment. You see in this typical plot the cross-section of for spin-independent scattering of a typical WIMP as a function of the assumed mass of such a particle. And the blue islands here are the signal reported by DAMA. One, if you predominantly observe recoils of the sodium, and then another island if you predominantly observe recoils of iodine, because it's obviously sodium iodide and you have two materials in the target. And a lot of experiments really exclude this with almost absolute certainty. And since 2 years, there is also the COSINUS experiment, which uses also sodium iodide crystals as a target material, so it has the same target material. And this experiment was also able to put very strong constraints on this signal. But one has to say that all of the other experiments have a different target material, so it would be a very nice thing to have a direct search with the same target material, which can absolutely clarify the situation and perhaps also say something about the nature of the signal measured by DAMA. Now, what actually is the DAMA experiment? Basically, it's an array of sodium iodide crystals which are read out via photomultipliers. So what they measure in the end is only the scintillation light. So if you imagine a particle doing an interaction in the crystal, then you will see some scintillation light, and this is measured via a photomultiplier. So since they only have one readout channel, they cannot perform any sort of event discrimination. So you don't know if the interacting particle was actually a charged particle or a neutral particle, or whether the interaction happened with the nucleus or the electrons in the crystal lattice. And it also means that they can only define their threshold in terms of keV electron equivalent, meaning that if you have an electron which deposits 10% of its energy from the interaction in scintillation light, then you will only measure 1 keV in scintillation light, and then the original energy might have been something like 10 keV. So the idea of COSINUS is now to employ this very well-known technique and technology from CREST to improve the readout of sodium iodide as a detector material. You see it on the left side. So instead of just measuring the scintillation light, the idea is to measure the phonon signal. So if an interaction happens in the crystal, if a recoil happens, then you would measure the heat signal, which is a phonon signal, and then the phonons propagate through, in this case, a carrier crystal to a transition edge sensor, which is basically just a superconducting film. And the scintillation light is measured via an additional channel, which is in this prototype, which you see here, a silicon beaker, which serves as the light absorber. And you see also on the lower left side the first prototypes which we built. The transparent thing obviously is the target crystal, and then afterwards it's covered with this silicon beaker, which is used for the light detection. Now, if you measure the phonon signal directly, you will have not only a much lower threshold because you measure more of the energy which was deposited in the interaction, but you will also have an additional channel which gives you particle discrimination. So you can determine which particle actually made the interaction and whether this interaction happened as a recoil or whether you had some interaction with the electrons. The idea is that we will construct detectors on the same performance level like you have them in the second phase of CREST, with something like 1 keV of nuclear recoil energy threshold. Sodium iodide has some very peculiar properties. First of all, it's hygroscopic, meaning that if you just expose the crystal to air, the surface will degrade and you will not be able to measure anything. So you have to handle it in a controlled atmosphere. And secondly, we don't actually know a lot about the scintillation process. If you operate sodium iodide at room temperature, you need thallium as a dopant in the crystal to actually observe the scintillation. But it's not really clear what happens now if you cool down the whole thing and apply it as a cryogenic detector. So whether this thallium is actually required or whether it even impedes the scintillation process. So this is one of the great unknowns and what we call this the quenching factor mystery. If you look at this plot on the lower right side, there are a lot of different measurements which have quite some variation. And obviously, if the quenching is stronger, you will have a better particle discrimination in an experiment which can actually see this quenching. Yeah, and then there's another thing, which is a contamination of the material with potassium. Many experiments actually employ a liquid scintillator veto around these crystals to tag the gamma, which is produced in this decay, to then veto the Auger electrons at low energies. So this contamination can actually become a problem. And you have to keep it in mind when operating these crystals. The crystals which we use in COSINUS are mainly produced by the Shanghai Institute of Ceramics in China. And with the crystals they are producing, we arrive at purity levels which are comparable to those of DAMA and even lower. So we can basically test different crystals with different potassium contaminations and also with different thallium doping, to see basically what happens and how they influence on the quenching factors and on the scintillation light yield. There's a very nice publication from them. They don't only produce crystals for us, but also for the LIBRA experiment. And now let me show you how an actual signal in the COSINUS detector would look like. This is a simulation for something like 100 kilogram days of exposure. And what you see on the y-axis in this plot is the ratio between the signal measured in the light detector and the signal measured in the phonon detector. And this is plotted as a function of the signal in the phonon detector, basically. And then What you see is a simulated background which is flat with a potassium contamination comparable to that in the Dharma experiments. And all of these events would show up at this electron gamma band up here. So these events would have the highest light yield. And if the signal which Dharma is measuring actually is a WIMP, it should show up in the nuclear recoil bands down here. So you see in blue and green the bands which are displayed, which basically use some quenching factors from literature. And the red dots are a simulation which is consistent with the WIMP model, which best fits to the observed Dharma excess. So this is from a publication from Savage at Altre, I think from 2013. Yeah, so if we really should see the same signal as Dharma, we should be able to separate it very clearly using this light yield representation and employing two readout channels. This is some data from the first prototype, which we built. You see now on the y-axis the light energy directly, not the yield, but the light energy. And on the x-axis, the energy in the phonon channel, so the channel from the absorber crystal. You see the electron gamma band with some peaks from an americium source. And you see examples how pulses look in the detector. This is a scale of several hundred milliseconds, so it's a very slow signal. We perform a low background and search, a rare event search, and you have to operate the detectors basically in a low background environment. Otherwise, the signals will be too, otherwise the rate will be too high since the signals are long. This is data from the second prototype, now again in this light yield distribution. And this second prototype already had a threshold for the absorber crystal of something like 8 keV. If you remember, I told you that the design goal would be something like 1 keV. And yeah, you see here at 6 keV or something, the potassium line. So this is a line from the potassium contamination. And you see, again, these peaks from an americium source and also an iodine escape line. And down here you see events which happen in the carrier crystal of the module. So if you remember, I told you that we don't only have the sodium crystal, but also a carrier crystal on top of it, which then carries the TES sensor. One more thing that I should say is that since we do a counting experiment in the end, we have also some model independent sensitivity. So if you simply consider the rate of events which you measure, then you might make some statement about other dark matter particle models or the other halo models, whatever. Experiments such as Dharma basically measure a modulation, so it's a variation of a constant rate, and you need to have a constant rate to have the modulation. So if you just do a counting experiment, you can make some more general statements. And there is a very nice paper from Felix Karlhöfer at Altre, published 2 years ago, which explores this idea. This last slide basically shows the roadmap for COSINUS for the next years. On the right side, you see an image of the planned setup. So you have some office building on the left side with construction space for the detectors, which will be a clean room. And then you have the water tank on the right side. And in the middle of the water tank, there will be the cryostat shielded by some layers of copper. And in the cryostat, there will be the modules for the COSINUS experiment. And if everything goes well, we are planning to gain something like 100 kilogram days of exposure in the first phase, with which we will be then able to say something about the nuclear recoil origin of the Dharma modulation, like whether the particles which they are seeing are WIMP-like or not. And if this phase goes on for a little bit more, we might be able to put some model-independent constraints. Yeah, and then if we see something, there might be the second phase where we do some modulation analysis if we actually see a signal and if there is a modulation to see. To be fair, one should also say that there is quite a competition with sodium iodide direct detection experiments now. COSINUS is only the most recent one. And yeah, the most prominent of those would be NaI's, COSINUS, and LIBRA, which is still in construction. And there are already quite a lot of results from COSINUS and from NaI's. But up-to-date COSINUS is the only experiment which will feature multiple readout channels and therefore particle discrimination. So this is a very unique characteristic. This brings me to the summary. So the COSINUS experiment will start basically the construction in next year with the construction of the water tank in February. We have a lot of prototype measurements, which we did in the last years. We were already able to apply sodium iodide crystals as cryogenic calorimeters or bolometers with several readout channels, which allows for particle discrimination. And if everything goes well, we will have some results for the standard WIMP scenario within the next years. And a very unique characteristic of the experiment is that we have the ability to cross-check the results from DAMA in a model-independent way. Thank you.